何が出てみたいな。次は、
それが何回か繰り返し、今まで知られている常識的なものではない。うん、なんだろう、的な話に、新しいなものと無理
ですよね。
そういう、そういう人がそう、実はこういう、そういう意味では、差が出ない。
全部違うものでなければ。
仮想的に、的の、する。
いや、期待っていうか、いや、何実態を見えない。
そういうが別になるんです。だけど、
うん。
So first of all, this is my second time visiting my experience. So let me remind you of the definition of the singularity category, which is actually that's also the same as the one in we only consider the congregation. So let her be your responsibility. Okay. And then I use the notation DSGR, not SGR. The DSGR is by definition where the opposite of the bound is divided by the finally generated are modules by so by definition, this is again a triangulated category, and there's basic properties of the category. I only need two of them. The first, let's satisfy the form. So for any object that's in the SPR, there is a case of finitely generated module n and the integer n such that x is like morphic to in this category x is like morphic to m shifted by n. Okay. Actually speaking, every object is just module in this category. The second property is for any finitely generated module then and any non-negative integer then this module m is subject to it's an physics shift variance. So this one is and physics. So using these two properties, we can show that for example, if R is 1 point, then every object is morphed to a shift of maximum point. If R is 1 point, then you can take n to x, you take n large enough, then omega n becomes and I think the most celebrated result of singularity category is again it was a dimension. So, he proved that if he wants if R is one thing with finite two dimension, then as Osama mentioned, Osama said, in this case, category of point modules, or more precisely, category of maximum point modules becomes a Frobenius exact category, and the stable category is triangulated. And using your category, that's where you equivalent a triangulated category to the stable category. This is, I think, more celebrated with the singularity category.
Like you mentioned, we can coordination.
In this talk, I only deal with coordination. Oh, I will also deal with other dimensions, but anyway, if I write dimension of the ring, then it means the curl dimension. Okay. And Orlov has been studying the singularity categories in relation to mirror symmetry, homological mirror symmetry. I think many of you are familiar with this stuff. I don't know. So anyway, this is about basic people for mainly I will discuss I will to discuss the generation in this time. So to do this, let me remind you of the notation introduced by Wonder Fountain. So the T is a general triangle. That's way. Then for each object x in T, and an integer non-negative integers n. We denote by bracket x n plus 1 to be the collection of objects of E which are built, which can be built out of X. From X by taking several operations. First, finite diverse sums. And second, direct sums. Shifts, translations, and most any maximum form. Okay. We should notice that this number is here. So this is for some technical reason. So here is n, here is n. And then we also define the generation time of x to be the infinite of the integers n, such that the bracket x sub n plus 1 is actually equal to t. So this measures the time for x to generate over the generation. So, and in what form we will often think of the following situation, not always, but often. Let me give it the second. Yeah. So in the sector, R is a local ring, which has dimension D, so current dimension D. And I also assume that complete, A is complete, and equal characteristic. Which means that R and K have the same characteristic or equivalently are contains a field. And coincidentally, isolated singularity with K bar. So in the setup, we only think of the such a case. R is a local ring, which has dimension D, and so we also see that R is complete, coincidentally. These two assumptions are actually can be extended or not generalized. In fact, in some cases we can replace this complete with excellent, but in some cases we don't need coincidence. But for simplicity, let me assume. And then so-called coin structure. So, R is a small picture, quotient of saving over K of some finite remaining form of our series. And here, this number, the number of variables E, and then E, the definition. Minimal. And also, we can apply for Jacobian criteria. So, now we identify with this wing, then I need to Jacobian. So the Jacobian idea is by definition the idea of R generated by or the C minus of the Jacobian matrix. So C is the codimension, emerging codimension. So we can define such an idea of law. And then by using the Jacobian criterion, the Jacobian idea is the defining idea of the singular locus. But we assume that the ring is isolated singularity, so the Jacobian idea is then primary. So I mean, the Turing algebra. We are more Jacobian. The Lady length of our video is fine. It's everything Lady. So this one is Jacobian. One is regular. But the Lady length is fine.
It is the same as being finite dimensional.
Yes, right. And the Lady length means the minimum number, minimum power of the maximum idea. Minimum number where maximum idea to minimum or infimum integers such that m of the Jacobian idea to the end. So this is number is theta arm of Jacobian. And we also denote how to be the power of generator. The Jacobian. So this is our set.
Geometric. Is there any geometric meaning of this term?
In a type socket, this is actually just a so it's if like if in a type of socket, then it is just the number is e. There is a geometric meaning. Anyway, these numbers, what I want to fix, emphasize is that this number is defined given by. So it's the invariant. So now let me use some example of generation. First, let's consider such simple ring kx not x to the n. Kx denotes the polynomial ring in one way, where k appears. Okay. And then by the structure theorem of finitely generated modules over principal ideal domain, we can easily see that there are only finitely many indecomposable modules. Indecomposable finitely generated modules. And in fact, they are R of x, R of x squared, R of x and minus. There are only n composable modules. And then takes G to be the direct sum of all these modules. R plus R of x plus x to be minus 1. Then still this is a finitely generated R module. And as I told you at the beginning of this talk, every object in a singularity category is isomorphic to a shift of some finitely generated module. So using this part, we can easily see the singularity category of R. It's just given by bracket G sub 1. It means that every object in this category, as I said, every object in this category is a shift of a module. But every module is a direct sum of finite direct sum of copies of G. So we can obtain every object in this category by from G to taking finite direct sum shift only. So we don't need any mapping in this case. So the number is 1, n is 0. So the generation time of G is. And what generally yes, because R is early. Any Artinian maybe is for. And actually this can be extended to the quantum case. I mean, if R is quantum point,
and all this modules are correct. This here.
Yeah. So every module, every finitely generated module over an Artinian ring is one. So if R is Cohen-Macaulay ring of finite representation, or more precisely, finite Cohen-Macaulay representation, which means that there are infinitely many Cohen-Macaulay modules. Within universe. In this case, again, we can apply the same argument. So G is just the direct sum of all indecomposable Cohen-Macaulay modules. Still, this is finitely generated because there are only finitely many such modules. And then the same argument shows that BSGR is again in sub 1. As I said, every module, every object in the singularity category is isomorphic to a shift of a coin code. We can take such coin. So in this case, again, the generation time is G. Exactly. This is due to supervised Ryo Takahashi, 1987, and explicitly given in my joint work with Arcadia. The quotient of the form of series ring in two variables over field K, any field K, by x squared. Then there are infinitely many polynomial modules over this ring, but still we can classify. So the book by Gloyer and Schreier classify all the polynomial indecomposable polynomial modules over this ring. So we can, by using this classification, we can show that for any polynomial module, then there is a Schrodinger sequence of the form. So it is exact. We can construct such a Schrodinger sequence. So any polynomial module is a direct sum of an extension of some finite direct sums of copies of R. So in this case, BSGR is bracket R of X sub 2. So we need one extension. So one extension, each extension corresponds to a mapping form. So we just by taking one mapping form, we can obtain every object in this category. So here, assumptions. So, and also we can show that the maximum ideal is not in R of X sub 1. So GT of R of X is equal to finally, this is the final example, which is due to Bala, Pavelo, Cavallo, and down myself, and Jian Liu. So if R is as in the setup, if R is such a case, if R is satisfied with this condition, then the generation time of the rescue field K is also a module, so we can take on the which is up to R minus T plus 1 times L minus. So R is here, the number of generators of the Jacobian radial, L is the Levy length of the Turing algebra, and E is the Crew dimension. So we have such an outcome squeezing them. So this is not very possible, but Anyway, we can bound, so the generation time of the velocity field can be bounded. In particular, this is fine. Remind you of the definition of Orlov spectrum for a triangle data. Again, it can be any triangle category. And then all spec of P is by relation the set of all generation but only five. So all spec P denotes such a set. So, but only we collect only finite generation. So this is actually a subset of the set of non-negative integers. And this is all wrong.
So this condition of isolated singularity, the singularity category is whole finite.
In a Goretti case, yeah, in the non-words, we only assume that the ring is quite. So then
Here, it somehow is generated by K with
yeah,
whole finite.
every object can be obtained from K by taking those operations, taking diagonals, shifts.
And it is whole finite. From K to K, when you generate this finite dimensional whole.
Even home from K to K, I don't think it is.
Concrete intersection.
So in the Goretti case, it is home. So DSGR is, as I said, by book by result. In the Goretti case, the singularity category is equivalent to the stable category of point modules. And the stable category of point modules is always. So in this case, in the Goretti case, it is finite. In the non-Goretti case, I think it's never. I don't know. It is no. And also T and the dimension, the Riccier dimension. This is the dimension of triangle. So this is by definition the infimum of all of spectra of T. Riccier dimension. Okay. This has been studied widely and deeply. Dimensional or Riccier dimension. We can also define screen modeling. This screen. And this also has a name, UD. Screen model for step T. And this is called the Archimedes. Topology.
So we define it.
Actually, only very almost nothing is known. Maybe it's I should say so. Yeah, there is almost nothing known dimension. But I will give you some results on finiteness of finiteness of ultimate dimension is not in the title. Only for finger. Secondly, this is only for local means. How is the logic commutative necessary observing? And then we newly introduced the following invariant, which I wanted to go to dx, which is defined incremental integer then. K, K belongs to x and any non-zero. Yes. We try to for dominant index. So this is an invariant for and this is the R is uniformly long. If this number is fine. So we don't know if this number is fine in general. But if the number is this is finite, then we call R dominant uniformly long. So this didn't have a name. So this notion didn't have a name so far, but essentially it was studied by Ballard in the catalog. In fact, they proved in the same paper. Okay. In the same paper, they proved that if R is three-dimensional hypersurface, so if R is a local hypersurface, dimension D, then they prove that the dominant index of R is no equal to 1. It's fine. So any hypersurface is uniformly dominant. And moreover, they also proved that if R is as in spectra, namely R has an isolated singularity, complete equal characteristic, blah blah blah. In this case, they also showed the form. The form any non-zero object in the singularity category, the generation time of x is at the most 2 times d plus 2 L minus d.
Sorry. This definition dx, right? It's increment over what?
Increment of integers. Since that
Meaning
belongs
over
to
each or x or n
n.
for given
N is non-negative integer.
x
X runs all non-zero.
is increment over all x
Yeah.
and n. I mean, for instance, if x is not a generator, then
So maybe
so you infinite
if So in front of such an integer n, that which satisfies this condition.
Right, but there is an x.
Yeah, x run all over zero.
If you over all such x.
Over all such. This doesn't say that. That doesn't necessarily say that x is a generator of DSG.
Why x
Easy to figure this. That was how that one. So I need to take all non-zero objects, not only K, but also any other. And then K. So basically, if we cannot find, so if K does not belong to the C closure of X, or n for some X, then this is infinite. This number is infinite.
It's not continuous. Yes, it's level over x. You have n and k. You should put there and you also have x. So
Fusing point is x of dx is just index.
this is yeah, it's confusing. It's okay. I'm speaking about capital X. In your brackets, there is x and n, and then when you put this in whatever, you should put. You take this.
N, because there you have for any x, it's over n.
Yes.
About it's infimum. It's infimum over n or over x.
Infinite over K. Over X.
Over x. I mean, because if you just take x to be k, you get some triviality. So probably take supreme over x.
It's not over
n over x, n sub x, then it will be clear. N depending.
The problem is take x to be k, you got something zero.
This has to be satisfied for any x,
Yeah.
not only for k.
Not only.
What's
So if K, if there is only, so K is the only object of this, then we can say X to be K. Then in that case, this number.
So finiteness of dr implies a very strong conclusion. For example, any six sub non-zero six subcategory contains K. For example. Yeah, so this is a bit unusual definition.
We ask stupid question. K is a quotient field. K.
Yes.
So you can simply quotient field.
In the harmony.
So you mean k belongs to x n for all x half all x.
Yeah. What she said. So if this number is okay, then any object, if it is E, if this is delta, for example, then it is finite. If it is finite and this number is delta, then you find you get that K belongs to all objects, non-zero object, for any non-zero object. K belongs to X times delta plus. And in fact, in the hypersurface case, this is up to D percent. So they proved it. And if we also assume that there is an isolated singularity with some mild conditions, then the generation time any non-zero object X of DSGR is up to this number. So, and this number is, of course, this number is already finite. So any non-zero object is has finite generation time, which means that any non-zero object of the singularity category is a generator. And also, this number is independent of the choice of x. In this case, ultimate dimension of ESTR is also up to this number, which is 1. And I think this is the only known thing about finiteness of ultimate of the triangle. And indeed, in the equation, however, Volkov also say that this is the first large class of examples where the ultimate dimension is 1. Okay. So here is if let's go back to uniform domain. Why do I call this uniform domain? It means three ways. If R is uniformly dominant, then in sense of my previous paper published in 2023. And I don't give the definition of dominance, but instead let me give some properties of some conclusions. So, R is so-called for an X friendly in the sense of triangle. That's it. And say about this stuff. Original training and stuff. Namely, there are only trivial vanishing of openings. Namely, if you have vanishing of all in sufficiently large degree, where M and N are finitely generated module, then either M has finite projective dimension, nor N has finite projective dimension. Okay. So once we have such vanishing, then the trivial conclusion. So we have a trivial conclusion. Namely, the other way. So the converse is always true. So if M has finite projective dimension, then for Mn is 0 for degree larger than projective dimension. So that right hand side and left hand side. These two conditions are equivalent. So this means that tall friendly. And the X friendly is defined that similarly. Okay. So this implies that BGM is finite or IBM is finite. IBM denotes the injective dimension. Okay, so uniform dominance gives you such decisive properties. Okay. So for example, so-called the unsupervised conjecture. which is a long-standing conjecture in commutative algebra. For such a. So if R is uniformly dominant, there are only trivial vanishing of X. So in particular, Gaussian writing conjecture for such a ring. So there are many such, but several other decisive properties uniformly dominant. So we can classify.
For conjecture, they have many conjectures. Which one? This is about.
So if you have a or positive mixed vanishing, then M is true. So we still need to argue that so even if R is X friendly, it implies that M has finite projective dimension, but we can also show that M. If this part is finite injective dimension, then for inner again, we can show it clearly. So, and also, we have some classification results, so I don't have enough time to explain the reason of examples. So, such decisive statements hold for any uniformly dominant group ring. So a natural question asks whether when is your ring commutative Newtonian ring R or local ring R uniformly dominant? And ring with this is a partial.
This conjecture implies conjecture about finiteistic dimension.
In commutative case, finiteistic dimension conjecture is trivial. The finiteistic dimension conjecture only meaning to be the non-commutative. Commutative setting, so the finiteistic dimension is up to the depth, so it's always this one. Domain theorem. So then again, let now be any local ring, and let me put E to be the embedding dimension, and E to be the depth of like the input. So if the ring is going for it, E is equal to the current dimension. In this case, first, if A is an element in the maximum ideal, which is R regular, so non-zero divisor, then we have the point. So dx, so maybe dr, so dr mod dr at most 2 times dr mod a plus, and the dr mod a is at most dr. If a is not in the square of we have such inequalities. So in particular, this number is finite. If this number is finite, then this number. This number is finite, then this. So if R of A is uniformly dominant, then so is R. And the converse also true. If A is outside of the last line, square. And using these two properties, we can also show that if R is uniformly dominant, if and only any formal power series ring over R is uniformly dominant. And we think we understand that completion, M-adic completion of R is uniform. So this is the first statement.
They just realize this finiteness for complete intersection.
Is in the complete intersection. We certainly. In this direction only holds if A is outside. So the regular sequence is outside of the square. So general complete intersection is not such. What ring is this size? What ring is the uniform result? It hundred so-called birds. I think I don't think it. I think no one knows. So no one here knows this. I don't give the definition, but for example, if R is a hypersurface, then or if R is coinatory, then it's minimal then R is good. So for example, rational surface singularity is the virtual or several other class of commutative local rings which are not unknown to be Birch. Okay. So if R is Birch, then dx of R is more 2 to the E to T plus 4 minus 1. So E is the embedding dimension, T is the depth. In particular, this number is finite. So in this case, R is uniformly. Any Birch ring is a uniformly dominant. So any hypersurface is uniformly dominant. But already it is known the theorem. But you can extend it to Birch rings.
And minimal multiplicity means what?
Minimal multiplicity means the Hilbert-Samuel multiplicity of R is always bigger than or equal to the codimension of R, embedding codimension of R plus. So we always have this inequality. And then minimal multiplicity means this equality.
Quite restricted, right?
Yeah, but if the ring has rational surface singularity, then it is minimum multiplicity. And I think basically all fine point local rings of finite representation type minimum multiplicity in at least in dimension bigger than. In a Gorentz case, this implies that the ring is. So maybe in this sense it's less brief. And also if M is if M mod some regular sequence is decomposable as a normal. Then again, the dominant index of R is at most 2 to D to T plus 3 minus 9. And again, in this case, now is uniformly dominant. So by using these two statements, we can construct many examples of uniformly dominant local. And finally, final treatment of our main theorem.
Decompose
The nouns.
as these two.
So there is no period composition. And X plus or non-zero mode.
At least two.
To at least two non-zero. You can take any regular thing. So you can modify. You can modify by any regular thing. But in that case, if such a quotient is between then it's uniform. So I restrict, let us restrict to the set. Then and also assumes R is uniformly dominant in this case. So I want to sufficient condition of uniform dominance. With dominant in the extent. Then the generation for any non-zero object from the singularity category, non-zero object, singularity category, the generation time of x is up to 1, n plus 1 times r minus plus 1. So again, this is so and this number is independent of the choice of. So again, we have a finiteness of the argument dimension. The singularity. So the only essentially
Is this DOR?
E bar is E bar E is an inclusion, sorry. So I already erased the set. In the set, E is a coordinate bar. In the number of generators from the Japanese idea. So it also gives you the concept of local rings, which whose singularity categories have finite order space. Okay, thank you very much. Any question?
Calculated by this technique. Not just there.
Yeah, in some cases, like one cover of compute all the oral spectrum. The actually dictate the oral spectrum of the singularity category in AN singular case. So AD, not AD, only AN singular. And I think Makehara also decided or spectrum EN thing. He didn't. He has not yet.
Just one very nice question. So, how many people study ultimate dimension or Orlov spectra?
Why? Because I don't know.
Thinking about in Freeman means natural. Thinking about the Rugier dimensions is looks more natural. How many people study? The other possible now. Generation things and one.
We know that through alpha dimension.
I remember that I did Kazako one more. But I think it's some conjecture that this somehow controls whether that is additional So Marital proposes power chipset. There's some gaps and this gaps depend on whether you're saying you can find code over as you find code over some you are actually is to bring this conjecture is like
There is an explicit conjecture.
yes.
Thank you.
We have an Intel cover to R, an Intel cover from SM to Rn. Is there some relationship between the spectrum? Yes. No related study. No related study about this. How behavior under descent for
I'm not actually, I truly know that in this case, so, actually, so you need to work with in, Germany. I don't know. What makes sense?